Hi guys, welcome to another video for our synoptic meteorology class. So we talked about atmospheric stability and other topics. So considering that the atmosphere is unstable and clouds form, what's next? So we'll just talk about just that in this video. So this video is about precipitation, its process, and its type. So first, let us define what is precipitation. Okay. Precipitation is any liquid or frozen water that forms in the atmosphere and falls back to the earth. It comes in many forms like rain, sleet, and snow, and in so many forms that we'll be talking about later on. So then again, it's a liquid or frozen water. Along with the evaporation and condensation in the hydrologic cycle, precipitation is one of the three major parts of the global water cycle. It is important to note that the intensity and duration of precipitation are extremely variable in most areas of the world. So, if you're already in the field, you'll be asked as to how much rain fell, but you cannot answer them if how long it will take for the rain to stop or for how long any kind of precipitation will be. And so let's talk about where does it start? The growth of precipitation particles. So first, we know that condensation of water vapor in the atmosphere provides water droplets and ice crystals and clouds. These precipitation particles are denser than the surrounding air and falls at a rate of few centimeters per second. These precipitation particles will either evaporate or will be held suspended by vertical currents within the cloud. So these precipitation particles alone are not enough to produce the precipitation that we experience or see at the surface, like rain, or snow and such. They'll only reach the ground if they become large enough to stand evaporative processes and overcome upward air motion. So um, the illustration at the right part of the slide, you can see that the typical raindrop is 2 millimeters and the typical cloud droplet or the precipitation particle is just about 0.02 millimeters. So that's really small. And this typical cloud droplet will not be able to reach the ground because it will either evaporate and will be held by vertical currents within the cloud or what we call updrafts. So condensation begins on particles called condensation nuclei, or in many studies, cloud condensation nuclei. So this cloud condensation nuclei can be aerosols, can be particles, very small particles that will start or that can start condensation. And so the typical cloud droplet, as I've mentioned a while ago, this only has a diameter of 0.02 millimeter. That's less than a thousandth of an inch. So that's really very small and 100 times smaller than the typical raindrop. So the growth of cloud droplet is slow and may take several days even under ideal conditions. So, knowing that condensation alone cannot enlarge this typical cloud droplet to a typical raindrop size that is able to reach the ground, so we need other processes to explain it. So, there are two important processes of how rain is produced. One is the collision coalescence process, or the process that takes place for warm clouds, which we'll be talking about later on, as well as the ice crystal or the Bergeron process. Okay, so let's move to collision coalescence process. So this process is for warm clouds. In clouds with tops warmer than 15 degrees Celsius, the collision coalescence process can play a significant role in producing precipitation. To produce the many collisions needed to form a raindrop, some cloud droplets must be larger than others. So large droplets can form on large cloud condensation nuclei such as aerosols, salt, suspended salt particles, fine sand, and many others. So even in many studies, we are now looking at what we call giant condensation nuclei that can either inhibit and make condensation progress. And so larger drops fall faster than smaller drops. So we know that large droplets overtake and collide with smaller drops in their path. So this fall merges droplets through collision called coalescence. So that's what is depicted in the illustration. If updraft is strong or the strong vertical wind, smaller droplets will be pushed upward, then coalescence can happen quicker. So you can see the red small arrows pointing up. So that's what we mean by updraft. That is pushing smaller droplets upward, making it collide with larger droplets. Coalescence is enhanced if colliding droplets have opposite charges. Laboratory studies show that collision doesn't always guarantee coalescence, as these droplets can bounce or they may bounce apart during collision. Or there is what we call surface tension. So this surface tension holds the cloud droplet together. So this force may be too strong. So they are not able to coalesce even if they collide. Next. The amount of time the droplet spends on the cloud is an important factor influencing cloud droplet growth. So strong updrafts can maximize the time spent by the eh, droplet in the cloud and size of growth. So clouds that have above freezing temperatures at all levels are called warm clouds. So in other words, if the droplet stays longer within the cloud, so there is a larger chance for it to grow much bigger. So warm clouds, as I've told you a while ago, clouds that have above freezing temperatures. So these are also clouds that is only in the liquid phase. Again, cloud that is only in the liquid phase. Levels are not present with temperature below freezing level. So that's why we call them warm clouds. And so the most important factor in production of raindrops is the liquid's water content. So also we have other significant factors such as the range of cloud droplet sizes. So if we have a variety of droplet size, like we have small sizes, we have larger ones, then we can expect that droplet growth is quicker, as I've mentioned a while ago. Also, cloud thickness and the updrafts of clouds. So talking about cloud thickness and updrafts of clouds, so there is a case between cumulus clouds and stratus clouds. So with cumulus having a large thickness and stratus just flattened layers of clouds, we can say that cumulus can produce large rain droplets because this can actually be viable for more collisions and coalescence to happen as compared to stratus clouds, which only has thin layers. This only produces, if it can produce precipitation, this only produces drizzles caused by weak updrafts and thin and small thickness. And so next significant factor, we have the electric charge of droplets and the electric field in the cloud. And so we can say that the droplet concentration is really crucial in the rate of growth of droplets. The droplet concentration is determined by the balance between the rate of supply of vapor by cooling. So when we say rate of supply of vapor by cooling, that's condensation, and the rate at which it is removed by deposition. So maybe you're aware of deposition. So deposition just means it's a phase change from gas to solid, or we can call this desublimation. Also, the concentration of droplets will be reduced by the entrainment of dry air from the environment. So, what is that what we call entrainment of dry air? This just means that it's the mixing of environmental air into an air current or cloud. So dry air mixing with uh, moist air, what does it do? It actually causes the air to get colder. And when it becomes colder, it becomes heavier. So this costs, I mean, this causes downdrafts or the winds going down as compared to updrafts. Okay. Droplets can grow rapidly by condensation in relatively unpolluted regions than in clouds in highly concentrated cloud droplets. Growth rate of droplets by concentration decreases as the radius increases. So moving on to the point above, droplets can grow rapidly by condensation in relatively unpolluted regions than in clouds in highly concentrated droplets. So more CCNs or cloud condensation nuclei or pollutants wherein these water vapor can cling onto to make a larger droplet. So more CCNs, this distributes water to many smaller raindrops. So that's one of the factors that we look into local weather, wherein the more pollutants that we have, the less likely it will rain because it distributes water vapor into so many smaller drops and inhibiting uh, droplet growth to sizes that are possible for it to be able to reach the surface. So that's collision coalescence process. Again, this process is for warm clouds or for clouds that has above freezing temperature. So now we go to the ice crystal process. So what is this ice crystal process? So ice crystal process of rain formation proposes that both ice crystals and liquid cloud droplet are present in clouds below freezing temperatures. So this rain formation is important at mid latitudes and high latitudes as these temperatures can go below freezing level. So that's what we call cold clouds, so below freezing temperatures. In 1911, Wegener proposed that rain was formed by melting of ice particles. Ice crystal process is also called the Wegener Bergeron Feindesen process, or shortened as what we call the Bergeron process. So here we can see the distribution of ice and water in the typical cumulonimbus clouds, or in the previous video, cumulonimbus incus, having the anvil top. So you can see that from the surface to you can see the line of the freezing level. So below that line of freezing level, we can say that the particles present is only liquid water. So also above the 7,600 meter line, we can say that only ice or glaciated. So temperatures go at about -40 degrees Celsius. So that's way below freezing level. But in between those lines, we can see that, and we can say that there's a mix of ice and water. So temperatures can go to negative 20 degrees Celsius. So, in this middle layer of the cumulonimbus cloud, the water particles are actually super cooled water. Laboratory studies actually shows that smaller amount of pure water, so the smaller amount of pure water, the lower the temperature at which water freezes. Cloud droplets are very small. It takes very low temperatures for it to form or to become ice. Ice crystal process. Ice crystals can form in subfreezing air if there are ice-forming particles present called ice nuclei. The number of ice-forming nuclei available in the atmosphere is small, especially at temperatures above negative 10 degrees Celsius. So how is snow formed if ice nuclei or ice nucleus are very small in the environment? Liquid cloud droplets can freeze, but only at very low temperatures, as I've mentioned a while ago. Also, liquid cloud droplets, ice nuclei can initiate the growth of ice crystals, but they do not abound in nature. So let's just talk about the ice formation in cold clouds. So given the illustration at the right, air is saturated for both the liquid droplet and ice crystal, and they are in equilibrium. So we have a uniform temperature of about 15 degrees, negative 15 degrees Celsius. And so we can say that the number of molecules leaving the surface of both the droplet and the ice crystal must be equal to the number of molecules returning, since it should equalize or be in equilibrium even if there are molecules and leaving the surface of both the liquid droplet and the ice droplet. Again, more vapor molecules above liquid than ice, as you can see, because it's easier to escape in the liquid droplet than in ice. So remember that ice is solid, so it's really very difficult for molecules to leave the surface of ice as compared to molecules leaving the surface of water vapor. It takes more vapor molecules to saturate the air directly above the water droplet it than it does to saturate the air directly above the ice crystal. So since it is in equilibrium, whatever is leaving should be replaced. So at the same subfreezing temperature, the saturation vapor pressure just above the water surface is greater than the saturation vapor pressure above the ice surface. And so the difference in saturation vapor pressure causes water vapor molecules to move from the droplet towards the ice crystal in the process that we know, which is diffusion. So as you can see, the removal of water vapor molecules reduces the vapor pressure above the droplet. Since the droplet is now out of equilibrium with its surrounding, it evaporates to replenish the diminished supply of water vapor above it. This provides a continuous source of moisture for the ice crystals, which absorbs the water vapor and grows rapidly. So, during the ice crystal or the Bergeron process, ice crystals grow larger at the expense of the surrounding water droplets. So, those water droplets that has been out of equilibrium, they evaporate, and the molecules from the water droplet diffuses towards the ice crystal. So that provides the needed supply of water to the ice for it to grow to larger sizes. Ice crystals can grow even larger through accretion. So that's the more of a static way or stable way of um, making the droplet or the ice crystal size larger. But we can also, but ice crystals also grow even larger through accretion. So accretion is where ice crystals collide with supercooled droplets and stick together. So this makes Gropal, which is a kind of precipitation or snow pellets. So falling Gropal may fracture and provide seeds for ice formation in cold clouds. So remember that in these clouds, even if it's warm or cold, there is collision. And so this falling Gropal or even snow pellets, when they are colliding with other ice particles, they either stick together or they fracture and provide seeds for ice formation in cold clouds. So what I mean by saying seeds is that this can provide or this can actually form or serve as a cloud condensation nuclei for it to form another uh, ice particle, and so there is a chain reaction. So collision, breaking apart or sticking together, this small particle that breaks apart, um, they provide seeds or starters, which is a better word, starters for new ice formation in cold clouds. Rains in mid and high latitude starts as snowflakes or snows or ice particles, and they just melted as they fall. Again, so this is an illustration of that. So in the first picture, diagram A, falling ice crystals may freeze supercooled droplets on contact. So that's accretion producing larger ice particles. Next, falling ice particles may collide and fracture into tiny secondary ice particles. So falling ice crystals may collide and stick to other ice crystals, aggregation or the process of aggregation producing snowflakes. So knowing the process of warm clouds and cold clouds, we now talk about precipitation types. First, we know, or the precipitation type that is so very well known to us is rain. Rain is a falling drop of liquid water with a diameter equal to or greater than zero point 0.5 millimeters or zero point 0.2 of an inch. So, so that's how you consider precipitation rain. So drop of liquid water with a specific diameter. So smaller than this, we can now consider them as drizzle. Also, we can say or pictured here, streaks of precipitation that evaporate before reaching the ground is called virga. So I'd just like to remind everyone that in the hydrologic cycle, this processes actually happens at the same time. So there is condensation, there is also evaporation that happens. So a precipitation can fall down, and before falling down, it can evaporate. And so these streaks of precipitation that evaporate before reaching the ground, they are called virga. So raindrops held by updrafts and suddenly fall are called rain showers. So these are usually brief and sporadic. So this can be in small patches of in a location. And if they are excessively heavy, they are called cloud bursts. So this rain showers, so looking at the diagram below, This can actually render a local or a place having a side which is dry and the other side as um, wet because of the rain. Because the other side may be the location wherein there is an updraft, and the other side they can experience the downdraft. So that's rain. Simple. Next is snow. Snow, precipitation, which is composed of white or translucent ice crystals, chiefly in complex branch hexagonal form and often agglomerated into snowflakes. When ice crystals and snowflakes fall from high cirrus clouds, they are called fall streaks. So, as pictured, this is a fall streak. The bending of the streaks is due to the changing wind speed and height. Also, with regards to snow, there's what we call blizzard. It's characterized by low temperatures and strong winds. So we cannot relate so much with blizzard since we are a tropical country, bearing large amounts of fine, dry, powdery particles of snow that reduces visibility to less than 1/4 mile and sometimes to as little as a few feet or at least 3 hours. Okay, so that's snow. How about sleet and freezing rain? So sleet and freezing rain, partially melted snowflakes or cold raindrop turned back into ice. So that's sleet. After falling through deep sub-freezing surface layer or air as tiny and translucent ice palette. So you can see the temperature, vertical temperature profile. So in the diagram, so snowflake coming from a nimbostratus cloud. So it's in a sub-freezing surface, but then it comes to a layer in the atmosphere that it's above freezing, so meaning it's warm. So what does it do to the snowflake? It melts the snowflake and it becomes a raindrop. But then it can go into another layer, which is a deep freezing or a sub freezing level, which then makes the raindrop freeze. And so that's what we call sleet. If the cold layer is shallow, or what we call, or what is pictured here as the deep freezing layer, what if it's shallow? So these may fall as super cold liquid drops. So they are not solid, they are not ice, they are super cooled liquid drops, which we can call as freezing rain. So when they reach the surface, they become ice. Also, when small supercooled cloud or fog droplets strike an object whose temperature is below freezing, the tiny droplets freeze, forming an accumulation of white or milky granular ice called rime. So you can see rime. So I think this is the same thing that we can see, though not the same process, in our freezers. So when there is a substantial accumulation of freezing rain, the result is an ice storm. And so this is the distribution, the vertical temperature profiles for the first four precipitation types that we talked about. First is snow. You can see that the air temperature is below freezing on all levels. So temperature is cold below freezing or sub-freezing. Next, we have the temperature profile for sleet. Zone of above freezing level melts the snowflake. Above freezing, so meaning warm. Deep sub-freezing air at the surface freezes it once again. Snowflakes or snow coming into a layer of above freezing, so it melts as a raindrop, then comes into a layer of sub-freezing temperature, so it becomes sleet, or it solidifies as an ice that we can call sleet. Next, we have freezing rain. Freezing rain, melted snowflakes become super cold liquid drops, freeze in contact, producing freezing rain. So the difference is that we have a very shallow freezing layer for the freezing rain. Next is we have rain, so just the opposite of um, snow. Air temp is above freezing in a sufficiently deep layer, so it produces rain. So it starts as snow or ice particles, but then the layer below it, or what we call sufficiently deep layer, is warm. So it melts and it is it stays that way as it reaches the surface. Next, we have snow grains and snow pellets. So these two are almost the same, but then snow grains are small, opaque grains of ice, the solid equivalent of drizzle. So these are really very small. They fall in small quantities from stratus clouds and never in the form of a shower. Upon striking a hard surface, they neither bounce nor shatter. Maybe like when you throw styroball, very small styroball. Next, we have snow pellets. These are white, opaque grains of ice about the size of an average raindrop. So this just the major difference between snow grain and pellets are the sizes between these two. So pictured here are snow pellets. They somehow look like salt. Next, we have the last precipitation type, which is hailstones. So hailstones are pieces of ice, either transparent or partially opaque, ranging in size from that of a small piece to that of a golf ball or larger. Some are round, others take on irregular shapes. So you can see pictured here below is hail. So many many crops are destroyed when there are hailstones, or what they call the white plague, actually, because this can even injure people or break windows, break car windows. They are really very destructive when it comes to farms, for when it comes to crops. So how does this happen, or how does this form? So as the growing ice particles pass through regions of varying liquid water content, a coating of ice forms around them, causing them to grow larger and larger. So actually, we can say that hailstones has been within the cloud, or held within the cloud, for a very long time, that they already collided with other ice particles, varying, or what we call here, the regions of varying liquid water content. So many examples of hailstones, they study hailstones, they cut it and they can see the cores or the layers within the hail, because as I've mentioned, it has now a coating of ice, since it has stayed in the cloud for so long by a very strong updraft. So they fall as hail stones. So that's it for precipitation process and types. So check the Google Classroom for the activity for precipitation. So that's it for um, this video. See you and study hard.